So here we have a sphere with a radius of 4, where there is a cylinder. So if you can see me move the cylinder, the size of the cylinder changes. Now the cylinder is inscribed in the sphere, meaning the circumference of the base of the cylinder is making full contact with the edges of the sphere. So I'm just going to turn this around, and as I change this shape, what happens with the cylinder? Well, when I go up higher, the height of the cylinder gets more, but the radius gets smaller. Or if I were to change the height, make it lower, so the height is smaller, but then the radius is larger. So the goal of this question is to figure out the maximum volume of the cylinder inscribed in this sphere of a radius of 4. If you take this app and move it around, you see different perspectives of the shape. So if I were to face this looking from the top, you see a circle in the circle. From a top point of view, one is the circle of the sphere, and then one is the circle of the cylinder. And I'm just going to make this back to 3D. And when you make it to 3D, looking from different perspectives, and what do you notice if I take it from this point of view? Imagine an axis face, that green thing facing you. So what you notice is it is actually a cross section. Imagine cutting the sphere in half, perfectly in half, like a hemisphere, semisphere. What do you notice? This seems like the 2D, it seems like it's a rectangle inscribed in a sphere. So when we actually start the algebraic approach to maximize the volume of the cylinder, we actually can take it from a 2D point of view. So the question for today is, what is the maximum volume of a cylinder inscribed in a sphere radius 4? So before we actually label our diagrams, let's start off with the function that we're going to optimize, which is the volume of a cylinder. So the volume of the cylinder is pi r squared h. And let's actually find r and h in our picture here. So when it comes to 3D in the top diagram, the radius here is from the bottom of the circle, the base of the cylinder, to over here. That's your radius here. I'll put r here. And the height of the cylinder is from the edge along here. So this would be your height. Now if we were to take this and cut the cylinder in half, so imagine you cutting along this axis here, you end up getting a cross section. So right here in the bottom you see a two-dimensional shape. Well, where is the radius and height in this? Well, the radius is from here to here, though. That would be your radius, put here in yellow, and the height would be this entire thing from the top to the bottom. Now let's actually figure out how radius 4 is involved. How would you label the radius 4? Well, in the three-dimensional shape on the top here, the radius actually starts from the center of the sphere to the edge. It's hard to think in terms of 3D, but I'm going to connect it from here to here, or it can be from here to here to the top. So there's many ways to draw radius. And when we take it from a side point of view, in this diagram over here, our radius is going to be from the center of the circle, which is over here, to the edge of the circle. So, but I'm not going to actually focus the edge from here to here, because I want to somehow connect the radius to something inside the cylinder, or in this case the rectangle, from a two-dimensional point of view. So I'm going to take a yellow line and start from here and go all the way up here. So that would be my radius, and I'm going to call this 4. So in the bottom two-dimensional shape, I'm just going to draw a triangle here. Now this 4 will never change. The sphere's radius is always 4, no matter how the cylinder changes in its height or in its radius. So what's happening, that there's a constraint with this triangle here. So from here to here is r, but from here to here is h over 2. In other words, there is a right angled triangle that will not change in terms of its relationship with each other, meaning the Pythagorean relationship. So in other words, 4 squared is equals to r squared plus half the height squared. And if we just expand, we end up getting this following. So now we have a choice right now, going back to the original question, the volume. Do you want to express volume in terms of r or in volume in terms of h? You have two choices. And in my case, I'm going to express it v in terms of h. There is a reason why, because if you notice here, I have r squared. And if you notice here, over here, I have r squared. In other words, I can replace the r squared with 16 minus h squared over 4. And if I did that, my function in terms of h would be pi h, and inside the r squared, it gets replaced with 16 minus h squared over 4. And if I were to expand this, this would become a 16 pi h minus pi h cubed over 4. And here we have a cubic function, which we can take the derivative using the power rule. Now, if I were to do the other way around, if I were to actually isolate for h, what's going to happen is that I'm not going to do it in this. I'm not going to show you in this this segment, but you're going to get a square root, and then it's more difficult to take a square root derivative and work with it than dealing with a cubic function. So let's talk a bit about the restrictions of the height. I'm not going to show you this in an algebraic point of view. I'm just going to show you from a more of a graphical standpoint. What is the lowest that the h can be in order for a cylinder to exist? Well, the h has to be greater than 0. Now, in this picture here, because the cylinder is constrained by the size of this circle, the sphere, well, what's the maximum height of the cylinder? Well, the maximum height of the cylinder cannot surpass the diameter of the sphere, which is 4 plus 4, which is 8. So the last thing you need to do is, number 1, find the first derivative, do your first derivative test, or you can do your second derivative test to prove it's a maximum. Put here maximum, and then you got to prove that it is show me that it's an absolute maximum, like between 0 and h, by checking the end behaviors, or in this case the end points or the limits as h approaches 0 and 8.